Hi kids, it's Mrs. Geiger here. So we're going to continue on talking about kinetics. And in this video, what we're going to talk about is something called a potential energy diagram. Now remember, potential energy is stored energy or chemical energy. It's the energy we say is stored in the bonds. Just like how when you have magnets and they stick together, or when you get your sock out, you get your laundry out of the dryer and your sock gets stuck to your pants. That's because of the electrostatic force holding it together. So there's some amount of potential energy there. So in this diagram, what this shows is the potential energy changes over time. But instead of saying time, we say something called reaction coordinate. Now, all that means is that if we really made it time, some graphs might be smushed together and some might be really spread out. So we kind of change it to this other term, which just means that it's metered by how fast the reaction goes. So we always get a nice smooth curve. So what this reaction is talking about is from the beginning of the reaction on the left to the end of the reaction on the right here. So what you'll see here is that, what you'll see here is that on the y-axis, we have potential energy. All right. So you should go ahead and draw this in your notes. I would give myself an entire page for this diagram. All right. And so what you need to do is make it look like what I'm going to call a fun roller coaster. You're going to start with the reactants high up. Those reactants should have a flat amount of energy because the reaction has not started yet. Then you're going to go up. Now, the reason we go up is because we need to break the bonds in the reactants. So when we break the bonds in the reactants, that always is going to take energy. Because remember, when particles get further apart, energy is absorbed. It is always going to take energy to break a bond. So the graph will always go up first. And then we get to this peak, the crest. And we call that crest the activated complex. So over here, you're going to label reactants. At the top of your crest, it's going to be called the activated complex. The activated complex is something that exists for a split second in time, and it is between where the reactants are pulled apart and the new products are formed. It's the tipping point of the reaction to occur. Then you're going to go woo all the way downhill to the products. Now remember, when products are formed, new bonds are made. So that's always going to be exothermic. So the shape of the graph will always go up and then go down in terms of energy. Now let's talk about these bars I have in green. Those bars I have in green represent different amounts of energies. Right? The y-axis is the energy axis, and the x-axis is the time axis. So we're talking about how the energy changes over time. So I just have here the 3 points all the way down to the x-axis. I have that labeled as potential energy of the reactants, potential energy of the activated complex, and the potential energy of the product. I'll just move myself over here. The potential energy of the products there. So those are 3 amounts of energy. So there's 3 points: reactants, activated complex, products. And there are 5 amounts of energy: potential energy of the reactants, potential energy of the activated complex, and the potential energy of the products. There's 2 other amounts of energy. This first amount of energy is the amount of energy it takes to get the reaction going. That is the amount of energy it takes to go from the reactants up to the activated complex. And that EA stands for activation energy. So I'm going to go ahead and put that over here. That is called activation Ooh, sorry, that looks terrible. I have to fix that. All right, activation energy, and I'll just do it like this. It's labeled E sub A because it's a type of energy, right? And what type of energy? Activation energy. So that's why we label it an E. It's a type of energy. And then we use the term activation there. All right. So there's one other amount of energy that you need to know, and that is the enthalpy of the reaction. And you'll notice that that's the net energy here. It's between the products and the reactants. So it's from the endpoints to the starting point. All right, so that's going to be the amount of energy here. You'll notice that this is an exothermic potential energy diagram. All right, I have exothermic up here. In this exothermic potential energy diagram, the reactants have more energy than the products. So that means that energy is lost or released when the reaction occurs. There's a net loss of energy to the environment. All right, we're going to do it all again, but for endothermic. So here is my endothermic potential energy diagram. And what you'll notice that's different in my endothermic potential energy diagram is that my reactants start out low and my products end up higher. So go ahead and draw, you can pause the video and go ahead and draw this. The y-axis is still potential energy and the x-axis is still reaction coordinate. But what you should see here is that the reactants start here, go up to the activated complex, and then come down to the product. And the products end up with more energy than the reactants started with. So go ahead and pause the video and copy this down. All right, so we're back. So what you should see here is that the potential energy of the reactants is less than the potential energy of the product. So when you take the potential energy of your products and you subtract the potential energy of the reactants, your delta H here is a positive value. To go from the reactants up to the products, the substance is needed to gain energy. Now what you'll also notice is that the activation energy is in the same place. It's from the reactants up to the top of the activated complex. This is bond breaking, always endothermic. This is bond making, always exothermic. So still the shape of the graph is the same, but in an endothermic reaction, the reactants start out with less energy and the products end up with more energy. So how does this, what would this look like if we had a catalyst? A catalyst is something that we say creates an alternative reaction pathway. Remember we talked about a catalyst in the last video, and we said that a catalyst is a helper that is not used up, but it helps the reaction to happen faster. You can think of it like a shortcut for the reaction. So if this is an exothermic potential energy diagram, it is. I drew it exothermic because I like exothermic reactions better. Who doesn't? So you'll notice that the energy to make the activated complex decreases, but the delta H is not affected. So it doesn't change the starting point and the ending point by creating this shortcut, but instead makes it so that the reactants can become the products using less energy. So the activation energy is lower, even though the enthalpy of the reaction does not change. All right, so hopefully you guys can read this, and because when I wrote this, it was... All right, so reversible reactions. We talked about this all year. We talked about reactions, and we did them forwards and backwards, and I'm going to go back to that copper sulfate pentahydrate example of the decomposition reaction. So reversible reactions are reactions that can be undone, and when they're undone, the amount of energy is the same, but the sign is opposite. So the enthalpy of the forward reaction has the same magnitude, but opposite sign of the reverse reaction. So what I have here is showing you the potential energy diagram of the forward reaction and the potential energy diagram of the same reaction, but in reverse, where you notice that the reactants are here, they become products, but if you reversed that reaction, the products would have the same amount of energy. These reactants would now be the products and vice versa. So your delta H, the amount of energy doesn't change, but instead the sign changes. All right, so let's do some practice problems. All right, so we are going to be using table I, and we are going to be doing some stoichiometry based on table I. All right, so you're going to be pausing the video and writing this down. So go ahead and do that now. All right, great, we're back. So example 1 is that the reaction below represents the reaction between carbon and hydrogen. So I took this off of table I, and what you'll see here is that it says so this reaction is endothermic, and for every 1 mole of C2H2 that's produced, we're going to need 227.4 kilojoules of heat. So that's the cost of the reaction. That's how much energy it takes for this reaction to occur. Because remember, we have to break the bonds in the solid carbon. So if this is coal, that will cost a lot of energy. All right. So I'm going to get my calculator handy and go ahead and do these problems. So find your calculator and make sure you have table I ready because we're going to do some math. Yay. All right. So if 682 kilojoules of heat are absorbed, how many moles of C2H2 would be produced? So just like we did before, you can set up a proportion or you can use dimensional analysis to do this. I'm just going to use a proportion because I just find it to be really simple in this to use a proportion. So I'm going to go ahead and move myself down here. And then we're going to say, okay, remember when we did the mole to mole ratio and we did this, we said 2 to 1. Now here the number is the same, 227.4 kilojoules. And then there's going to be 1 mole here. So those can be your denominators. Now, let's think about what we're going to put in our numerators. So we have this 682 kilojoules. So we're going to put that above our heat term, 682.2 kilojoules. And then how many moles of C2H2 are produced? So my unknown goes here. So you're going to end up with a ratio of 682.2 kilojoules divided by 227.4 kilojoules, and that's going to be what? Over 1 mole. So go ahead and solve that. Right, and you should have seen that this would make 3 moles of C2H2. All right, so the same idea, the ratio is the same, but you can think of it like that's how much energy it takes to make 1 mole. So if you had 3 times as much energy, you would be able to run the reaction 3 times and make 3 moles. All right, a little bit harder now. All right, so this says, determine the amount of heat released when 3.0 moles of aluminum oxide is formed from its elements. So you have table I handy, right? What kind of reaction is that describing? You got it, it's a synthesis reaction. So find where the synthesis reactions are on table I, and then find the reaction where aluminum oxide is formed from its elements. All right, great. So now that you have it, I'm just going to peek back here at my table I for us so that I can show you on my screen that we're going to be recording this reaction. So is this reaction endothermic or exothermic? You got it. It's exothermic. Great. And you know that because it has a negative 3,351 kilojoules of heat are given off every time this compound is created. So we're going to rewrite this in our notes, and then we're going to work on this problem and figure out how much energy is going to be given off here. So let's just go ahead and get back to, get back to where we were. Okay, so I'm going to just copy down the reaction, and I'm going to put the heat term into this reaction as I copy it down. So remember, it's exothermic, so that means that that heat is going to be a product. So I'm going to leave off the states of matter because it's not really needed in this problem, and it's just going to take up room. So I'm going to say 4 moles of aluminum react with 3 moles of oxygen to form 2 moles of Al2O3, which is aluminum oxide, plus 3,351 kilojoules. All right, so now let's do our problem. Determine the amount of heat released when 3 moles of aluminum oxide is formed from its elements. So I'm going to go ahead and set up a proportion again. And I'm going to say, well, I'm going to have 3 in my numerator, right, because that's given to me. And in my problem here, I have 2 moles. That's going to be equal to how much energy over 3,351 kilojoules. So go ahead and solve that problem. All right, great. So you should have gotten 5,026.5 kilojoules. By the way, you can absolutely use dimensional analysis to do this as well. You can put 3 moles out front, and you can multiply by a fraction where you're going to want to get rid of the 2 moles. You're going to put that in the denominator. And you're going to put 3,351 kilojoules in your numerator, and that will give you the same answer in kilojoules, and your moles will cancel with moles. Mathematically, it's identical as setting up a proportion and cross-multiplying, but you should have gotten 5,026.5 kilojoules in any case. All right, a little bit harder now. All right, you have to use table I again. So this question says, determine the amount of heat that is required to dissolve 20.0 grams of potassium nitrate. Express your answer in joules. All right, so first things first is potassium nitrate. What is the formula for potassium nitrate? You got it, KNO3. All right, so let's go ahead and on table I find the reaction for the dissolving of KNO3. All right, I knew I picked this reaction for a reason, so you should already have it in your notes that KNO3 solid plus 34.89 kilojoules over water. So you are going to recopy this reaction down. Magic. All right, so now that I have my reaction here, I don't have grams though in the problem. I have moles. So there's going to be a step before I can figure out how many moles I'm starting with. You guessed it. So go ahead and figure out the formula mass of KNO3 and figure out how many moles 20 grams is for KNO3. Right, so you get like 0.19782 right, in your calculator. But we need to round to a reasonable number of sig figs. So I rounded this to 0.20. I used 101.1 as my formula mass for KNO3. So if you got a different value, but it rounds to the same, if it rounds to 0.20, you're fine. But I just wanted you to know that I'm going to use 0.20 for the rest of the problem. So you should use that if you're following along. All right, so now that I know that I have 0.20 moles of KNO3, how much heat is needed for that number of moles? I don't have a whole mole. I don't have 101.1 grams. So I'm going to do the same thing. I'm going to go ahead and set up my proportion. I'm going to say 0.20 moles of KNO3 over 1, what is that going to be equal to if I know that it takes 34.89 kilojoules for 1 mole? So go ahead and solve this. You should have gotten 6.98 kilojoules. As long as you got something that rounds to about 7 kilojoules, you should be good. So it's 1/5 of a mole, 20 grams instead of about 100 grams. And it is 1/5 as much energy. All right. So now let's just make this a little bit harder now. Oh, that's in kilojoules. What did the question ask for? Not in kilojoules. In joules. How could I forget? So I'm going to have to convert this answer into joules. So we do that by multiplying by 1,000. So this is going to be, oopsie, I'm still in this silly yellow color. This is going to be 6,980 joules. All right, so we can keep going with this problem. How much fun is this, right? All right, so let's go all the way back to Unit 1 and think about if KNO3 is dissolved in 100 grams of water, starting at 25 degrees Celsius, determine the final temperature of the water. Well, how would we do this? What equation do we have that we can use to figure out the change in temperature when heat is added? You guys got it. You're so smart. It's Q equals MC delta T. And you notice it's talking about water, so we can use our 4.18 there. All right, so here we're going to plug in 6,980 joules for Q. For the mass, I'm going to plug in 100 grams. For my specific heat capacity for water, oh, you guys are so good. You know it's 4.18 joules per grams degrees Celsius. And I'm going to leave my variable as delta T. Just because I think it's just a little easier to do it that way than to have the T final minus T initial there. All right, so now, how am I going to figure out the change in temperature? I can take my 6,980 and I can isolate my variable by dividing by 100 and then dividing by 4.18. So it's going to go up by 16.70 degrees Celsius. So the change in temperature is equal to 16.7 degrees Celsius. So if we started at 25, what would our final temperature be? So you can plug this in here. 16.7 is going to be equal to temperature final minus 25 degrees Celsius. Or you probably figured out that if you take your 16.7 and you add it to 25, you will get 41.7 degrees Celsius. All right. Cool, right? Oh, no, wait. That's hot. All right. So that's it for this today. And I hope that you enjoyed and learned a lot about about energy stoichiometry.